let's see. Let's start with our usual set of announcements. Most of you answered the poll the best we could do in terms of accommodating the most people are the following office hours. So I'll hold my office hours on Mondays from 3 to 4, and Anupam et al. Will have their office hours Wednesdays from 2 to 3. Okay? And we'll try to figure out what the right room is for this, considering we have a fairly big class. And given the timing of everything, what I decided, if it doesn't throw too much of a monkey wrench into everyone's, which haven't already set in your mind the schedule of when we're going to do your homework, we're going to have the homeworks due on Thursdays, given the office hours, okay? So the homeworks will be distributed on the web. I'll alert you to that through email to make sure you know it's posted, you can download it, and then it will be due in 1 week. And in Manuel's mailbox, all right? Anybody have any administrative issues accessing the website or lecture notes or anything else? Okay? Okay, good. All right, so last time we just got started, and we're thinking about the context of our course and what we're going to be studying over the course of the year, those of you who will be here both semesters. And so the subject of quantum optics is, as I say, a fairly broad subject, and how I like to define it, it is the study of quantum coherence with and of electromagnetic fields, okay? So sort of traditionally, one thinks about quantum optics as the study of non-classical light itself. And as we will see in the course of this semester, the notion of classical versus non-classical light is sort of synonymous with the question of quantum coherence in light itself. But quantum optics is more than that. It's also about the way in which we can manipulate matter with fields and create coherence in matter. So all of those things will be part of our discussion over the course of the year. And to get started on that, we were just reminding ourselves of some very basic things. And we're going to do some very basic things for, a week or two, just to get ourselves up to speed. When thinking about interference, conceptually, the best way to think about that is to think about an interferometer. And sort of the generic interferometer we like to draw in quantum optics is the so-called Mach-Zehnder interferometer. And so this is an interferometer for electromagnetic fields, and we write our electric field typically in terms of complex amplitudes. The intensity then is related to the square of the complex amplitude. And if we wrote down then, thinking about this interferometer with two output ports, we can ask about the intensity seen at either output port 1 or 2. Okay. And we did the little calculation on Monday, and if I've added another element here, so I imagine this to have some phase shifter in one arm of interferometer. I can think about that equivalently as I have an unbalanced interferometer with different lengths of the arms, or I could just think about it as making the lengths equal and I put in some phase shifter. Okay? And what we found last time, written out here now, is that the input and output, the output intensities at these two ports are related to the input intensity through the usual kind of interference terms that we get related to the phase difference. There's a little bit of a jargon that one can think about, we like to talk about in quantum information. We can call it this phase kickback. That is to say, what an interferometer does is it turns phase into amplitude. Okay? So we want to measure the phase. The way we do that is by interfering the two paths. Constructive and destructive interference then changes the intensity or the amplitude in a manner depending on that phase. And that's shown here. So we want to measure the phase. We do that by turning that phase information into amplitude information through the interferometer. Okay? Okay. Right. Just as a little aside, one of the things we talked about on Monday was how, if we thought about a symmetric 50-50 beam splitter in the context of a kind of matrix related to the scattering of fields coming in to the two ports and going out the two ports, that scattering matrix had this form. This was an example of an SU2 rotation matrix in a two-dimensional complex vector space. This is going to become very important in a week or so when we talk about really all two-level systems, that is to say two-dimensional complex spaces, like a spin one-half particle in quantum mechanics, is isomorphic to what's going on in this picture of two interfering paths in physical space in a Mach-Zehnder interferometer. So we should sort of keep that in mind as we abstractify our notions of quantum coherence from this, very concrete physical picture of waves traveling along two paths, two arms of interferometer, and an abstraction of interference of paths in Hilbert space. And we start moving in that direction here, when we start thinking about, okay, now, instead of thinking about this as classical electromagnetic wave, if we want to think about the field coming out of this laser, not in terms of waves, but in terms of particles, from our wave-particle duality in quantum mechanics. We think about them as particles, as we will see, because they are indivisible. That is to say, if I were to put two detectors on either side output port of this beam splitter, whereas the waves split 50% here and 50% here, the particle does not split. That is to say, if I were to have two detectors on each side of this output port of this beam splitter and look at a coincidence counter, then we would see nothing. There would be no coincidence, because either this detector goes click or that, but neither both at the same time. So in that sense, this is a particle. But it's also a wave, right? I mean, it's both. It's peanut butter and chocolate. You're of a certain generation, you knew two great tastes go great together, like chocolate is a Reese's Rule, but particles and waves. So, I'm not a big fan of chocolate, but anyway, so indeed, we would never see a detection at both sides of this output port. But if we recombine the paths and then put the detector here, if I then ask whether this detector or this detector goes click, well, if this phase shifter was 0, then this detector goes click 100% of the time. And that is inconsistent with thinking about this from the point of view of classical logic. Right? Because classically, we would say there's some probability to go here, and given the probability it went here, there's some probability for it to be transmitted or reflected. Right? Let's do that out. So, the idea here is that we say, all right, well, I associate to this kind of interferometer two processes. In one process, the photon was transmitted through the first beam splitter and reflected from the second beam splitter. And to that process, I assign some amplitude. And then there's a second process, which by the photon got reflected at the first beam splitter and then transmitted through the second beam splitter. And to that process, there is another amplitude I define. Okay. What quantum mechanics says is that to determine the probability of an outcome, I need to square the total amplitude, right? But the total amplitude is the sum of the amplitudes, which of course that. Yes, sir.
So these two processes actually have one reflection and one transmission. Can we define in such a way that there is two transmission and two reflection?
We need to think about, I mean, of course, there are different, what we're looking at here is a particular outcome. We're going to look at a particular experiment. The particular experiment is we send a photon into this interferometer, and we say we're looking for the probability that this detector goes click. There's only two ways that that can happen. These are them, right? If there is a different kind of outcome for which we're trying to calculate the probability, like a coincidence count, then indeed we'll have different combinations of reflections and transmissions. But for this particular outcome, these are the two processes. Okay. And of course, what we have here is quantum interference.
Could one of the stars be on the side too? And the circle, you got side 1 star, side 2, and side 2, side 1 star.
Oops. I did that last time too.
Yep.
Yes. And it's the quantum interference terms that, of course, define classical logic. If we have two independent processes, we should add the probabilities. But quantum mechanics says that when you have processes that are in principle indistinguishable, that is to say, there is nothing in the universe that I can check that has a record whether this process happened or this, then I must add the probability amplitudes and then square. And that interference defies classical logic. In classical logic, I should just add the probabilities. Now, we had a little puzzle at the end of last lecture, so let's just go back, see where we were there. I got some complaints for people who watch my podcast from God knows where that I don't erase the board long enough. Work on that. All right. I always get these weird, emails from some kid in India. When are you going to put the solution for problem set 7? It's fun. I love that. It's not anyway, all right. So we were looking at the following Duncan experiment, which is a real experiment that's done all the time these days. Suppose I have a UV laser, and I pump this magic crystal, which we call a Chi-2 crystal, which takes my UV photons, which are called the pump photons, which hit this crystal. And every once in a while, we get a spontaneous decay of this photon into 2 photons, which we call the signal and idler, such that the sum of these guys is equal to that, right? And if we could look at the degenerate case, where we've picked out, as we can, by putting certain pinholes here that pick out, as we will see next semester, a particular direction such that this guy are equal. We don't have to do that. Let's just consider that case that we have equal. So this might be a UV photon, and these are 2 infrared photons that add up total. Okay. So now what we're going to do is we have these. This is now 2 photons. This is not a beam splitter. This is not taking 1 photon and putting it through a beam splitter where it either goes here or here. This is 1 photon turning into 2 photons through a non-linear crystal. Okay. Now these 2 photons we're going to align. We're going to do this pinholes. We're going to have 2 mirrors and bounce these 2 photons, the daughter photons as they're called. They're twins. They're born almost simultaneously inside this crystal. So we call them twin photons. And if I could draw better, I can line this better. And I have now a 50-50 beam splitter of the kind that we just discussed in the Mach-Zehnder interferometer. And now I'm going to have 2 detectors here. And I'm going to have my coincidence counter as we thought about in the context of the individual photon, but now I have 2 photons. Okay? And so now I ask the question, what happens to this in this coincidence counter? Do I see the 2 photons emerging and simultaneously hitting these detectors and making them go click? And with what is the probability for that to happen? So how would I calculate that? Well, you've read the notes, maybe. We can think about it a little bit. As we just said, what we should do is we should think about what are the indistinguishable processes which can lead to the final event of coincidence. Okay? So there are coincidence occurs if one of the following I could have the following situation. Both of the photons bounce off the detector. I mean, bounce off the beam splitter and then hit the detector. Right? That's one possible way. Another possible way is they're both transmitted through the. In either of these cases, I should see both detectors go click and my coincidence counter will then let's go click. So how will these are two separate processes. They're in principle indistinguishable. There's nothing in the universe that stores information about which of these happens. So according to Feynman's rule, we should add the probability amplitudes for those two processes and then square to get the probability for that to happen. So what are the amplitudes for these two processes? Yeah?
Well, would add to 0.
It would. How do we see that?
You can just use your matrix equation for the 50-50 beam splitter.
Right. So process 1 here, the amplitude of this up to the overall propagation amplitude, which is the same in both cases. I have both of these guys reflecting, right? And in process 2, both of them transmit. Right? So the total amplitude in this case is p squared plus r squared. And as Matt reminded us, we had our matrix for the beam splitter where we had the transmission amplitude was 1/√2, and this guy had the fancy I in it, which of course is 0. So if I were to phase shift this by making a little delta L, and I can move the path difference between this, and I look at the coincidence counts as a function of delta L, what one finds is the following. When delta L is 0, I get no coincidence. And as I move this a little bit, what I see is the following. Now, why does this thing go, at some point, go up? Yeah.
So you can tell that the paths are different.
Right. So there could be another 2 photons that are born from another mother photon. Right? And these photons are distinguishable because they're born at different times. And that information is there. In some sense, this width here, which was, on the order of a femtosecond, is kind of the width of the photon. The duration. Even though this is a monochromatic field, it's kind of interesting. We'll come back to this. This photon, this is a broadband thing. There's got to be, if there's something in time, there's got to be a width and frequency, right? And in fact, this experiment is now quite famous. It's known as the Hahn-O-Mandel effect. Len Mandel was one of the godfathers of quantum optics, together with Glauber back in the day. Mandel sadly passed many years ago. Glauber just passed in December, sometimes known as HOM. Interestingly, this is now a very important effect, and something is used all the time in thinking about being able to manipulate non-classical light. But what they were most excited about in this is that they were able to measure the width of the photon. not the fact that this was a two-photon interference effect. That was just obvious to them. But now it's like, oh my God, there's a two-photon interference effect. Yeah.
Over there you have the absolute value, S1 absolute value of
Yeah,
the red
yeah.
but here they don't.
Well, no, I do. So that means the probability of coincidence is this, which is 0. I just didn't do that. So ultimately, I have to square the amplitude to get the probability. I didn't do that. Yeah, but you're absolutely right. You have to do that to get, but you know, I did that part without saying it. Very good. All right, so, you know, what we see here in some of these examples is that what distinguishes classical from non-classical light is a subtle business. There's kind of two quantum mechanical effects that we're looking at here. One is randomness. The fact that this detector or this one can go click randomly, right? And we also have interference. Now, both randomness and interference are things that happen in classical physics as well, right? I mean, we talked about the classical interferometer, and randomness, I mean, if we think about the Boltzmann kinetic theory of gases, is a theory of randomness with fluctuations in it. But those fluctuations are obeying classical statistics. So in order to kind of distinguish what we mean by classical versus non-classical light, it's very important for us to be able to first understand that we can see some certain kind of randomness and effects interference in classical physics too. And then be able to distinguish what is a truly quantum feature from one that's essentially classical. Now, as I said last time, it's more than just a question of categorizing. It's more than taxonomy. The difference between these essentially quantum and essentially classical phenomena has important implications for the capacity of that system to do something different. And that's one of the main reasons that we're interested in making that distinction. So in order to get at these differences, I want to just first quickly in this lecture and maybe a little bit of the next, do a sort of fast review of classical statistics and some important aspects that we will use in this course. Okay? And some of this will be fairly elementary, and some of it might be new to some of you. But we'll do it reasonably quickly. So, I'm not going to be particularly rigorous. I'm going to be physics rigorous on how we define these things. And I hope that's sufficiently satisfying for the majority of you. All right, so very quickly, let's think about we have some random variable, x, and it can take on possible values in a set. S. I can then assign a probability which we'll just loosely write as P of x, is the probability that the random variable x is some x in the set. The probability, of course, is a non-negative number by definition. If we have a discrete set, that is to say countable, so I might have some x sub i's labeled by some index I, then I'll write P sub I as P of x of I. The probability of having the ith value in the set. All right? And we normalize by summing these guys up to 1. Now, if I have a continuum, then of course we talk about a probability density. Which has the units, if x has dimensions, then this has the units of 1 over x. It's the probability per interval. So that P of x dx is the probability of x being between x and x plus dx. And then, of course, we would integrate to normalize over whatever the interval of x is. Talk about the expectation value. If I have some function of a random variable, then the expected value of f of x, if it's a discrete or make sure I'm thinking about all the things I want to say. Right. Very good. Right. So we talk about, of course, the moments of the distribution. The expected value of x to the n. The variance, or the statistical fluctuations, is equal to x minus the mean x squared, which is x squared squared. Now, these things are sometimes called the central moments. So if I call this thing delta x, then delta x to the n is called the central moment. And the variance is just the second order central moment. One often talks about to calculate the moments, we can do that in principle through a generating function. So let me define the function m of t as the expected value of e to the tx. Okay, let me define that function. That function is just equal to the sum over the probabilities, e to the t. When I write the sum, that can of course be sum or an integral, depending upon whether I'm talking about a discrete or continuous set of outcomes. And this is nothing more than t to the n over n factorial, the expected value of x to the n. Right? If I just take that exponential and expand it in a Taylor series, which means that in principle, I can calculate these moments in terms of derivatives of the generating function. So the nth order moment here is just the nth derivative of this function evaluated everywhere. Now, this is a formally correct statement, but in general, this may not be a convergent integral or series, so I might not be able to calculate that function. However, it's often more convenient then to go into the complex plane, and instead of thinking about t as a real variable, think about it as an imaginary variable. So let me define the function pi of k as m evaluated at t equals I times k, where k is real. So this is equal to the expected value of e to the I kx. Right? And now, because I'm sloppy, I'm going to treat it as a continuous variable, just because sometimes it's nice to look at that. Notice this function is nothing more than the Fourier transform of the probability distribution. Right? This is a Laplace transform, this is a Fourier transform. This function is known as the characteristic function. And it's just like the moment generating function, but with an imaginary parameter instead of a real parameter. Now, if p is a nice function, which is square normalizable, then this exists, right? Because you know the Fourier transform of a function, who when you square it and you integrate it, you get something that's finite. So this is a nice convergent function for probability. That's why we like to deal with this. And similarly, I mean, this guy is just ik to the n over n factorial times the nth moment. Doing, again, the Taylor series expansion of e to the I kx. So once again, I can extract the moments as derivatives now of the characteristic function. So if I take the derivative, the nth derivative of the characteristic function with respect to k, and now I have to divide by I over I to the power n, or minus I to the n, evaluated at k equals 0, that is a way of extracting the moments. Just out of curiosity, how many people have studied the characteristic function in any probability course? Just wondered how new We'll see it. Right. Another important set of expectation values beyond the moments are the cumulants. And they're defined in a kind of crazy way through the generating function itself. Okay? So let me consider the function k as a function of the parameter t, which is equal to the log of the generating function. So that's the log of the expected value of e to the I t x. Now I can, in principle, perform a Taylor series expansion of this object, and that too will have a power series in T with some coefficients, which we'll call k sub n. And these coefficients, through this definition, are the nth order cumulants. That's how they're defined. So, that's to say, similarly, I can extract these by taking this function, taking the nth order derivative, and saying t equals 0. I can also do that with the imaginary by taking the log of the characteristic function. And similarly, the nth order cumulants here are derivatives of this moment generating function. That's equivalent. All right. Very good. So, with a little bit of work, you could see the following. The first order cumulant is nothing more than the first moment. The second order cumulant is equal to the variance. That is to say, it is the second order central moment. The third order cumulant is nothing more than the central moment to the power of 3. The fourth order cumulant, and beyond. It's a mess. It's a combinatoric mess, and I hate nothing more than grant writing and cumulants. I mean, combinatorics. Combinatorics is my least favorite math subject. Just can't think in those terms. I wish I could. I had to work on it. But anyway, it's a mess, and you can look them up, but it's not a simple function at all. All right. Very good. All right, so at this point we talked about just a single random variable. We talked about multivariate So we can think about, for example, two random variables. We can talk about the joint probability distribution. this is statistically the variables are said to be statistically independent if the probability distribution factorizes. Now this is, again, sort of loose physics talk. When these functions need not be the same functions. I'm just denoting the function by knowing it's going to be a different function depending on what its argument is. But really, this should be a piece of x and a piece of y, right? There might be different functions of that variable, but often we don't write that down. We just kind of understand what function it is by what its argument is. Like that. So if the probability factorizes, then we say that the two variables are statistically independent. The probability of one is independent of the other. And of course, we define the conditional probability. The probability that x is x, given that y equals y, which is the probability like this, is defined to be the joint probability divided by the probability that y is true. And we define thus Bayes' rule, which says that I can invert this and find the probability that y is true given x. Well, that's equal to this, but this is equal to probability x given y times the probability of y over the probability of x. This, of course, well, we'll come back to it. Next, we want to talk about the marginal probability distribution. So I might want to ask, what's the probability that y is true, or y is equal to y, irrespective of the value of x. So I don't care what x is, I just want to know what the value of y is, x, drop that, I don't care. The way I do this is I have to add all the possible probabilities. So this is something actually I should have said, and let me just put a little aside over here. Suppose I have two subsets of my initial set that don't overlap. Their intersection is a null set. Okay. Then the probability that something in S is true or this is true, either one is what? Just the sum, right? That's logic. Right? So, if I want to find the probability that y is true irrespective of x, all I should do is add up all the joint probabilities for all possible values of x. And that is what's called the marginal probability. All right, let's see. Okay, so now we're going to generalize to n variables. And now so I have separate here x1, x2, x3. These are not the outcomes of the given. These are n different random variables. I can talk about the joint probability distribution. I can marginalize over any number of these values, right? So I can talk about the marginal distribution for, say, just the probability of x1, irrespective of the others. And in this case, what I'd have to do is sum over x2, x3, up to xn of the joint probability distribution. Or can marginalize over any subset of those variables. I can also talk now about the characteristic function. Chi now is a function of n variables, which is just the Fourier transform of the joint probability distribution. And I can define, thus, moments for the multivariate case in terms of derivatives, partial derivatives now with respect to the characteristic function. This is a multivariate function. So I can define and say and a two-point correlation function or moment by taking the derivative n times with respect to k sub I and m times with respect to k sub j, setting k equal to 0. So let's consider the following moment. I can think about a covariance. We talked about the variance. We reminded ourselves what the variance was for a single variable. The covariance is equal to the two-point correlation of these central moments. So that's equivalent to the expected value of xi minus the mean xi times xj minus the mean xj, which is, of course, equal to xi xj minus xi equals j. Multiply that out. Now, if we have statistically independent of all of these variables, x1 through xn, then what can we say about the covariance? It'll be 0 except when n equals j, right? So this thing will be the variance only if I equals j, and if I doesn't equal j, then the covariance is 0. Right. So let's see. If I also think about statistical independence, suppose I consider a random variable y, which is just x1 plus x2 plus xn. And now I want to know, for example, what is the expected value of y for this multivariate? Well, if this would be equal to right? And this object, of course, would be equal to the sum of the expected values of these guys if statistically independent. Right? Because in that case, how does this follow? Well, this guy would factorize into all those terms, and then each one would be a marginal over that particular variable. So this would be the sum over I, pi, xi, where these become the marginal probability distributions. If we have statistical independence. Similarly, if I looked at the variance in y by exactly the same arguments here, this is going to be equal to the sum of the variances of all the random variables. This is a very important fact, I'm sure you know this, that if you have statistically independent random variables, the total fluctuation is just the sum of the fluctuations of each of the individuals. But just to reemphasize that fact. They add in variance and not in RMS. All right, what's next? Cumulants. Let's talk about multivariate cumulants. So for example, let's think about two random variables. X and Y. Or X1 and X2. So, for example, let's suppose, as we did before, let me let y be the sum of these random variables. I can talk about the cumulant generating function for that value as the expected value of the log of the expected value of e to the t y, which is the log of e to the x1 plus x2, which is the log of e to the x21 x2. Right? So, if my two random variables are statistically independent, well then this expectation value factorizes because the probability distribution factorizes. Right? And that thus implies this is the log of this plus the log of that, which is the sum of the generating function for random variable 1 and random variable 2. So, what is the moral of this story? The moral of the story is that if I have two, or if I have statistically independent random variables, the cumulant add. We saw just one example of that here, which was the variance. The variance is an example of a cumulant. It's the second order cumulant. It's also true for the third order cumulant. So if I looked at the third order central moment of a sum of random variables, which are statistically independent, then that third order moment would just be the sum of the third order moments for each of those random variables, and upwards for all the combinatorics that I need to do. Okay. So that's one of the reasons we care about cumulants, is that cumulants add for statistically independent variables. All right, finally about this, just sort of all the definitions and reminders about general things about probability distribution. Let's just say a little bit more about the multivariate cumulants. So I can define the multivariate cumulant generating function. I always think cumulant should actually have it, but I don't think it does. Okay. Of t as the log of e to the t dot x t t1 t2 dot 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 n. So again, I can talk about the multivariate cumulants for example, this two-point cumulant in terms of the derivatives of the generating function these are partial derivatives. Evaluated at large. Yes, sir.
So over here the t's are the same, over here they're distinct. Is there a difference between these two things, or?
Yeah, this is a cumulant for one random variable.
Okay.
The random variable y. So I'm asking about that. There's a probability distribution over y. And for that random variable, there is the conjugate in the Laplace domain or in the Fourier domain, which is t. Okay? So this is a single random variable y, which itself is the sum of these two random variables. Okay? Whereas here I'm talking about something different. I'm saying let's talk about the generating function of multivariate cumulants. Now, it turns out with some combinatorics, you're going to do some of this for homework because I like to torture people. We won't do this, but something similar. This turns out to be, as I found on Wikipedia, the following. I will explain what all of this means now. So, what this formula says is I can find, oh, this is not correct. Sorry. This is equal to, this thing is equal to the cumulant k x1, x2. So this is the joint cumulant of all n variables. So what are these symbols? Pi here is the set of partitions, I'll explain that in a moment, of x1, and B is the list of blocks of the partition. And the magnitude of this is the number of blocks. So this is best explained by an example. Let's consider the following 3-point cumulant. So, I'm going to look at the cumulant as a moment between x1, x2, and x3. By this definition, this is the following. So, what we have is the set x1, x2, and we look at all the different ways we can partition that into boxes. I can put them all in the same box. I can put them into two different boxes, right? And I put this guy in one box and the box. Or I can put them into 3 different boxes. In this case, pi is 1. In this, let's just say the magnitude of pi is 1. In this case, the magnitude of pi is 3. In this case, the magnitude of pi is 2. All right? And then I just have these signs depending on a number of different ways to do that. Now, how would you possibly derive such a thing? Any thoughts? Where does that formula that I boxed, or where does it come from? Yeah.
It looks kind of like the inclusion-exclusion principle of like probabilities. I don't know.
The exclusion principle.
Yeah, like inclusion-exclusion.
Oh, exclusion. I'm not familiar with that. I mean, this is a kind of form of Wick's theorem, if you're familiar with that in quantum field theory. But this follows from this. You have to be able to just take derivatives of exponentials, and they come down, but you got to do all the combinatorics to count how you take those partial derivatives, the thing that I'm saying makes my stomach hurt. But that's what you got to do to get these minus signs and all those factorials and all of that, right?
So we can assume that pi is like a temperature and xi is the number of particles that are distributed in like a system, Grand Cantor.
Boy, do I want to say yes to that?
Just
yes. Obviously, there's some relationship of counting and putting things in boxes. When I say I'm not sure here, I'm not sure. Yeah, that's that's a helpful analogy. But at the end of the day, it's a combinatorial problem. But this is a useful situation because we might be the case, for example, as we will discuss, I guess, next week, that for a case, for example, for a multivariate but for Gaussian distributions, all cumulants greater than or equal to 3 are 0. And that thus allows us, in the case of a Gaussian, this would be 0. Which would say that my 3-point correlation function can be expressed in terms of 1 and 2-point correlation function. We do that all the time. So that means for the case of the Gaussian, as we will see and we'll remind ourselves, it's really only 1 and 2-point correlation functions that define everything. All higher order moments are just functions of 1 and 2-point correlation functions. In some sense, Gaussians are very complex. And if we just have Gaussian statistics, yeah, not much to them. A particular example of that is what I call Wick's theorem, which has some other name in mathematics that I don't know, which says the following. If I have a multivariate Gaussian, which we'll talk about more soon, and I look at the expectation value of a endpoint correlation function where I say I now have an even number of variables, okay? That this can be written as the product over all I and j. So for example, x1 x2, x3, x4 is equal to x1, x2, x3, x4 plus x1, x3, x2, x4 plus x1, x4, x2, x3, what have I missed? X. Is that all of them? One second partition. Okay. One goes with 2, 3, and 4. Got it. Okay, we'll stop there. And we will pick this up next time. And what we'll talk about next time, we'll remind ourselves of some basic probability distributions, the central limit theorem, and we'll talk about stochastic processes, where we have probabilities that are dependent on time. All right. Have a good afternoon.